this video, I'll show how we can improve the ADSR envelope we built previously. There's a few things I'd like to change. The first is the way that the envelope behaves when it gets retriggered. And this is easier to show than it is to explain. So let's just take a look at the panel view. And you'll notice that when I retrigger the envelope, if it's already playing, it starts over from 0. So right there, you see that? And that's just kind of an ugly glitch in the sound that's going to give you a click if you're playing audio while that happens. So I'd like to change the envelope so that it's always going to restart from whatever its current position is on a new envelope. So to do that, we can use something like we're using with the release stage at the bottom here, where we just take the last known output of the envelope and we'll use that as our beginning point. And instead of triggering that when the gate turns off, we'll trigger it when the gate turns on. And let's just check out the panel to make sure it works. Alright, so you see now when I restart a new envelope, it starts heading towards the velocity level from whatever its current position is, instead of restarting at 0. Alright, so natural sounds from the world around us that our ears are used to hearing don't tend to have these perfectly linear changes in amplitude like we're making with our envelope right now. And so to get something that sounds a little more natural to our ears, it's good to use a different shape rather than just a line between the 2 points for our envelope. And so next I'll show you how to make a simple exponential envelope generator. And the equation for that is going to be x to the a power times end subtract beginning plus beginning. And a there is going to be the curve coefficient, and I'll show you how that works in just a minute. So we'll subtract beginning from n, and we'll multiply it times this x to the y module we're going to make here. Now you have to be really careful with this macro. It's in the expert macro section under math. And as it says, it's x when x is greater than 0 to the y power. However, if you give x a really small value that's still greater than 0, it's going to give you some errors. So basically what I'm going to do is I'm going to compare x to 0.00001, and if it's greater than that, then we'll send it to the x to the y module. And if it's not, then we're just going to declare that x to the a power is equal to 0. And even though it might not technically be equal to 0 in that situation, it'll be so close that you won't really notice the difference. So this just kind of underscores how you need to be really careful about the built-in math functions in Core. They work very well, but they're often optimized in a way that they're just assuming you're going to use them properly instead of checking to make sure that you are and wasting that CPU. Alright, so we can multiply the output times beginning subtract n, and then we'll add beginning to the total, and that'll be it for implementing our equation. And I'm just going to store that value in a latch that gets triggered whenever we have a new x value, and that way any incoming beginning or end values won't affect the output. And lastly, we just need to set a curve value. If you give a curve value of 1, it's just going to give you a linear response, and if you give it a curve value of 2, you'll see it becomes a more exponential curve. And if you go less than 1, you'll get kind of a logarithmic sort of a curve. And as you can see, the attack phase is now exponential. And I think, but I'm not sure, that analog synths tend to have a logarithmic attack period using a value like 0.5. I'm not sure of that, but I think that's the way it works. Alright, so let's duplicate our new stage macro for the decay stage and attach things accordingly. And we'll see that when the beginning value is higher than our end value, that this is going to give us kind of a weird response. Which is not really exponential at all, and it's not really properly logarithmic either. It's kind of on its side. So to change this, we can actually change the order of the beginning and end inputs. So we'll put the end in the beginning input and the beginning in the end input. And you'll see this has an interesting effect of kind of reversing the signal from where we want it to go. And so what's happening here is we're going to want to actually, instead of having our x value range from 0 to 1, we're going to have it start at 1 and count backwards to 0. So we'll take the input and subtract it from 1. And we'll have our decay section. And of course, we can just duplicate our stage again for the release section and go through the same set of steps of reversing our values and subtracting x from 1. And it's also possible to make a stage macro that checks the beginning and end values and sorts them and the x value accordingly. But this just takes a little more CPU, and in this particular instance we already know which one is going to be higher than the other, so we don't really need to do that. But it does make for a good project if you want to make a more flexible envelope generator. Now we'll see the release also gives us an exponential response. Alright, so that's how to build an envelope with an adjustable curve for each section. In this video, I'll show you how to build a wavetable oscillator in Core. The first thing we're going to need is a table that represents a single cycle of a waveform. And to that end, I've built this simple primary macro here that accepts an audio input and outputs a pitch. I'm not going to go over this structure in too much detail, but I'll include it with the files that come with this series and show you how to use it really quick. It's a very simple module. Our table has 2048 elements, and we're using that number to calculate a pitch that will have exactly 2048 samples in a single cycle of the waveform. So we'll use this pitch output to control an oscillator, and as an example I'm going to use the triangle sync oscillator. You can use pretty much anything here. One thing to keep in mind is that waveforms with large discontinuities, such as a square wave or a sawtooth, don't necessarily translate very well into wavetables. So for example, with a saw wave, when the waveform restarts, it jumps from a value of around 1 to a value of around -1, and we're just not getting enough information of what's happening between those two sample points to stop it from aliasing. So the higher frequencies will alias really badly if you try to use a sawtooth or square wave here, but pretty much any other arbitrary waveform without a big jump in the continuity should work perfectly. And one thing to keep in mind is the wavetable macro I've designed here is monophonic, so just make sure any signal that you send to it is also mono. And again, this doesn't even have to be an oscillator. You could grab data from a sample or whatever, but if you use an oscillator, we're able to get kind of this clean cycle like you see here, where it's an exact cycle of the waveform. So once you have whatever audio you want to use as a wavetable feeding into the wavetable macro, you press a MIDI note and it will record the next 2048 samples into the table like I just did. And we can save that data into a wave file using the save button in properties right here. And I'm just going to name this file triangle. And now let's look how we can use the oscillator structure we built in Core in a previous tutorial to oscillate this wavetable. So this is the basic sine oscillator we built earlier. I'm just going to delete the sine function. And remember how we had the default n value equal to pi, which means that our phase accumulator is going to go from negative pi to pi. And I'm going to supply a different value of 0.5 for n, which means that now our phase accumulator is going to run from negative 0.5 to positive 0.5. And when we're done with the phase mod section, I'm going to add 0.5 to that value. So after adding 0.5, we're going to have a value that ranges from 0 to 1. And we're going to use this signal to drive our wavetable. So let's create a new macro with one input and one output. And inside this macro, we can load a table module up. You can find in the memory section. And the table is basically an array that you cannot write to. All you can do is read values from it. But it has this handy little table editor section in the function tab of the properties that you can use to load up a wave file into our table. And loading them as 32-bit files is fine. I don't think expanding up to 64 bits will help you in any way here. Alright, so next I'm going to use, also in the memory section, a size module to determine the size of this table. So if our table has 2048 values, we're going to have index values ranging from 0 to 2047. So I'm going to take the size of the array, the table, and subtract 1 from it. And then we'll multiply that times our incoming value from 0 to 1. So once these values have been multiplied, we'll have a value ranging from 0 to 2047. And we can use that value to read from our table. So one common consideration here is that once we've multiplied our value that can be anywhere from 0 to 1 times the size of the array, we're not going to end up with an exact index value. And very rarely are we going to get a value of like exactly a whole number. It's generally going to be a fraction in between these two values, between two values in the table. And you can interpolate between those two values and kind of fade between them if you'd like. But I find that it doesn't actually do a whole lot to improve the sound quality. And if you want to improve the sound quality, just using twice as many samples in your table works just as well and ends up being easier on the CPU for the most part. So I would suggest, if you need to get better quality out of this, just changing the size of the table, which is easy enough to do in the function tab of the properties for the audio table that we originally recorded our data into. Alright, so next I'm just going to set up our wavetable oscillator here and make sure that everything works, and just demonstrate it with a little bit of phase modulation as well. So we want to give it a frequency determined by the incoming pitch. I'm just going to use a really simple envelope here, nothing too fancy. And we have our triangle oscillator. So there might technically be a little bit more aliasing going on in this wavetable than there would be out of a triangle wave that you generated on the fly, but I think in general the difference should mostly be inaudible. And I'm just going to modulate the phase with a sine oscillator. Alright, so that's how to make a very basic wavetable oscillator. In this video, I'll show you how to make a very basic stutter glitch effect that sounds a little bit like this. Okay, so let's begin with a new ensemble and a new audio core cell. We're going to want a total of 3 inputs. One to determine whether the effect is on or off, one to determine the length of the stutter, and one to provide our audio input. So the on and the length inputs are going to both be event inputs. So Stutter Glitch is at its core a delay-based effect. So we're going to want an array to hold a selection of audio data for us to stutter. And I'm just going to give this array a size of 44,100, which is enough to hold 1 second of audio data. And obviously you can change that according to your desires. And we're going to want to use the size of this for a few different calculations. So I'm just going to use a size module and create a quick bus that can give us that number. And next, let's create a write macro from the expert macro section. And we'll use this to store data in our array. And we're going to need to build a counter in order to supply an index for our write module. And this is just a basic counter. We'll start with a read module clocked by the SRC. We will add 1 to the value, check to see if it's greater than our greatest possible value, and if it is, set it back to 0. Pretty basic. And just because our index value is going to be an integer, and there's no reason to really use floats here, I'm just going to set the whole structure to integer, the whole counter structure. So we're going to compare our index value to see if it's greater than or equal to n, because again, the maximum index of our array is actually going to be n minus 1 because the array index starts at 0. And I'll end up setting this up such that we're only going to write to the array when the effect is off. And that's just so that we're not writing over the space that we're trying to read from as we're stuttering. I'll show you how that works in just a little bit. So at this point, building these counters should kind of just be second nature. They're pretty simple, and like I said at the beginning, they're used for just about everything. Alright, so once we have our index value all set up here, we can use that to control the index of our array. And like I said, we only want to write to this array when the on value is greater than 0. So let's check to see if the effect is turned on by using a combination of a compare and router module. And we'll check to see if it's greater than 0. If it is, we're going to have the Boolean connection as a quick bus because we want to use it in a few different places. First, I just want to send a trigger effect when the effect is first turned on. And that's just so that we can get some initial values when we turn the effect on. And then we can use another router taking the same Boolean as an input to decide whether or not we are going to write to our array. So let's just duplicate the first one and get rid of the quick bus and change the input like so. And if the top input of the array doesn't receive a value, then it won't write to the current index. Alright, so that's how we write to our array. And next let's start talking about how we're going to read values from our array. So let's load up a read macro and connect the OBCs at the bottom. And if the effect is off, we just want to read out the same values that we're writing. So I'm just going to trigger I'm going to store the index in a latch and trigger it if the effect is off, and use that to control the index in that case. And if the effect is on, we'll use a different value in this top latch that I've created here. So once we connect this read module to an output, if we play some audio through this macro, this core cell, it's just going to play out the same audio that it gets in, which is exactly how we want the stutter glitch to react when it's off. And since we're creating a monophonic effect, we can get rid of the voice combiners and turn the number of voices down to 1. And just verify that we get sound through our macro here. Alright, so next let's set up the length input. And this is going to be a time in seconds. So we'll just multiply the input by the sample rate, and that'll give us the total number of samples that our stutter will last for. And we can just create a quick bus with that value. And the last thing we need to do is supply a value to read from the array when our effect is off. And in order to do this, we're going to need a second counter. So I'm going to duplicate the first. And we'll want to change a few things. We're going to change the name of the quick bus, of course. And we're going to change the maximum value. So before the maximum value was n, or the length of the array, and we're just going to change it to our quick bus that's giving us the length of our stutter glitch. And one thing that's going to be different about this counter is we want to restart it from 0 whenever we are turning the effect on. So I'm just going to use a latch and a write module to achieve this. And we'll just trigger the latch using the trigger quick bus whenever we receive a event telling us that the effect is on. Alright, so now things are going to get a little complicated, but I'll do my best to explain it thoroughly. We want to start looping our value when our effect turns on, and the starting point that we're going to choose is going to be the current index minus the length of our stutter. So let's subtract length from index. And we're going to store the value in a latch that is triggered when the effect turns on. So when the effect turns on, essentially we're going to choose this value as the starting point of our stutter. And then we'll add the value of our second counter to this value. And this value is going to range from 0 to length. So overall, the loop that we're going to have is going to start at index minus length, and it's going to end at the current index point when we turned the effect on. So once again, we will store the index in a latch and compare this value to the index. And if it's greater than the end point of the loop, then we will restart the loop again. So let's create the latch, we'll change the input to index, and we will trigger it whenever the effect turns on. Alright, so if we haven't exceeded this value, then we can just pass through this using a merge module. And if we have, then we'll use another latch to reset our value at index minus length. So this is just your basic if then else statement. And after all of this, it's actually still possible that our value coming out of the merge at the end here is going to be negative. And so the reason for that is we're starting our loop at index minus length. And these are arbitrary values. We don't know what index we're going to be currently writing to and reading from when we turn the effect on. We could be at index 10. We could have a length of, a few thousand even. So that would put us reading from a negative index. And if we try to read from a negative value in our array, it's not going to work properly, obviously. So a way that we can work around this is, once we've done all of our checks here, we can simply check to see if the value coming out of our merge module is less than 0. And if it is, then we will make some adjustments. And as I'm rewatching my work here, I'm noticing that I've used a compare greater than 0 module here, but that should be a greater than or equal to module. And I've highlighted the module that I mean, and I've also included this ensemble in the included files with this tutorial, so you can check to see the slightly corrected version there. Alright, so if we have gone less than 0, we're just going to add the total length of the array. If we haven't, we'll do nothing. We'll merge the two values together. And this is the index of our array when the effect is on. So we can supply the top latch down here with this value. So I'm just going to add a knob for the length, and we'll just turn the effect on whenever we have a new MIDI gate. Very simple control scheme for now. Alright, so I've forgotten to connect something, and when I'm trying to turn the effect on, nothing's happening at all. And you'll see we've supplied this last latch here with a value, but we've never actually triggered that value. So we need to use the upper output of this. It should work fine. Alright, so we're back with our Stutter Glitch macro here, and in this video I'll show how we can add another control element called speed that controls the speed of our audio playback whenever the effect is active. So let's give that a event input and a knob. And what we're going to do is, instead of adding this constant value of 1 here to our position every sample, we're going to add the speed value, which is going to be from a range of -1 to 1. And because we're no longer working exclusively with integers, we want to change all of these integer modules that we have added here into floats. Particularly make sure you don't forget the quick bus here, which just because it's being sent from a float module does not mean it's going to be a float itself. You have to change that manually. And another change I want to make is we're going to get rid of this I latch here altogether. And instead of restarting our value at 0 every time, we're simply going to subtract the length from our value. And so previously, whenever this value was true and we were resetting it at 0, it was going to be exactly equal to length. So this is not really changing it in that situation. It'll still act exactly the same. But what this is going to do is, when our speed is a fractional value, it's going to make sure that all of our loops stay the same length. Alright, so it works so far when the speed is positive, but we also want to make sure that we check to see if our position value here has gone negative. And that will allow us to have a negative speed or reverse. So instead of checking if we're greater than length here, we'll just check to see if it's less than 0. And if it is less than 0, instead of subtracting length, we're going to add length. So again, this is still going to keep us within the range of 0 to length. And this should make our reverse work as well. One thing I want to mention is that we're still translating this position value to an integer before we read out of our array. And we're not making any effort to interpolate between values, so the quality that we're going to get out of this particular macro is pretty low. And I'll show you in the next video some interpolation schemes we can use to improve the quality somewhat. Okay, so I'm back again with our Stutter Glitch macro here, and I've made some changes off screen to save you the tedium of watching me change a million different properties here. But basically, I've turned all of the currently highlighted modules to use floating point instead of integer signals, with the exception of this last I latch macro here, which is only ever accepting integers for input. And in this video, I'm going to focus on adding interpolation to our macro. And so since our speed and therefore our position pointer are now can hold fractional values like we added for in the previous video, we want to be able to read fractional values from our table as well. So if we're trying to read between sample point 6 and sample point 7, we're going to end up actually reading out both sample 6 and sample 7 and then crossfading between them. And to get an idea of how this works, we can check out some of the factory macros in the standard macro section. namely the delay 1 point and delay 2 point macros. And we're going to make some edits that mean that whenever the effect is on, we're going to be reading from our table 2 times. So I've just rearranged things here so that when the effect is off, we're still only reading from the table once, which should save us a negligible amount of CPU, but it's still worth doing. Okay, so if we load up the delay macro I was talking about, the 1 point delay is pretty much identical to what we were doing originally, where we have an integer for the index point, and we're just going to read out that integer. But the 2 point delay is a little more interesting. So we have a fractional index value. We have this module here, which splits the integer and the fractional parts of the value. And then we read between 2 sample points, and you finally use the crossfade module to interpolate between the 2 points. So I'm going to copy and paste the relevant macros here. And one thing to take note of is that now that we have we're going to be having several different array read modules. That means we can't use the sample rate clock to control when they're read from, or otherwise, this one is going to read out every time the effect is on or off, even though it's only supposed to read out when the effect is off. So I'm just going to replace the trigger input with the index input. And that'll solve that problem. And we'll do the same with this other read module I've created. So we're going to be crossfading between the point chosen by the integer output of our macro and integer +1. And we use the fractional value to morph between them. This is a very similar method to what we did when we were creating linear envelopes several videos back, where we chose the beginning and end point of an envelope stage and then just used linear interpolation to fade between them. And last thing to mention, I'm not going to deal with it now, but this value that we've added 1 to here, once we've added 1 to it, we have no assurance that it's still within a valid index range. We might have gone over the top by adding that extra 1 sample point. So here, theoretically, you should be checking to see if you've gone too high, and if so, subtracting n from the value. Okay, so that's how to do a basic linear interpolation. There's also a 4-point delay macro that you can find in the standard macro section, which contains a more sophisticated interpolation technique. It requires you, as the name implies, to read out 4 points from your array, but it can give you some better results for sure. In this video, I'll begin covering the partials framework, which is a set of macros and core cells released by native instruments, mainly for use with the sign bank and modal bank modules. I believe both Razor and Prism is based on this framework, though I haven't checked to make sure. To find the partials framework, simply search for it in the reactor user library. It should be one of the first things that comes up, if not the first thing. The partials framework is divided into several libraries intended for different functionalities. In this video, I'm going to cover the multiplexing library, which is used to create an event bus. An event bus is a way to carry the values of many different knobs or other parameters on a single reactor wire. And this is particularly useful because oftentimes you run up against the limit that exists where you can only have 40 inputs and outputs on a core cell or a macro. So sometimes you want to get more than 40 values into a given cell or macro, and the event bus is a perfect way to do that. So to begin with, let's talk about how to fit values into the event bus. We have two sets of macros for this. We have the B event bus macros and the E event bus macros. And the E macros are easier to use, so let's begin with those. So each value on an event bus is given its own index. And so as you can see, we have inputs numbered from 0 to 9 here, and those are going to be added to the base index value, which is the top input. So if we leave the top input blank here, the events coming into this event bus macro are going to have indices from 0 to 9. So now let's create a core cell, and we can run the values of all three of our knobs here into this core cell using a single wire out of our event bus. And once inside the core cell, we can use a macro called the raw receiver to unpack our event bus data. So there are two of these. There's just the raw receiver macro, and then there's the small raw receiver macro. And the small version works great with the E event bus because it just kind of gets rid of some extra stuff that we're not going to use off of the normal version. And this event bus is going to receive values on indices 2, 3, and 4. So once we have the data unpacked, we can use another macro called the receive gate. And again, there's a regular receive gate and a small receive gate. We can use the small version. And we can connect the index and the value to the receive gate. So the index is the top event called ID, and the value is going to be coming through on the $sign here, which is a little counterintuitive. I kind of wish all these inputs and outputs labeled with $signs just said value or val or something. It would be a lot easier to remember. But anyway, at the top of the receive gate, we have an input which tells us which index we want to receive with this gate. So for example, if we give it a value of 2, then we're going to receive our 2 knob value at this receive gate, which we can verify by creating a numeric readout. So this particular example is really not doing much. We're simply packing all of our data into an event bus and then unpacking it and reading it into a numeric readout. But you can use this same technique to do a lot of really cool things that you would ordinarily would be very difficult or impossible. So this is working, and of course if we change the index here to 3, then we'll receive the knob at the 3 input instead. Okay, so our event bus can currently fit 10 values, but it's really easy to expand this capacity. So we have the E multiplex 10 module here. And if we create another one, we can simply connect the index output of the first one into the index input of the second one. And our second multiplexer here is going to have index values from 10 to 19. And we can simply merge the outputs together. And now we have an event bus with 20 values. Alright, so next let's check out the B event bus. And the first thing I want to note is that if we simply delete the E bus we have now and replace it with a B macro, we'll find that our code no longer works. And this has to do with the inner functionings of the partials framework here. So when we want to send a new value on the event bus is expecting several different numbers from us. First of all, it's expecting the index of the event. Then it's expecting to know how many values are arriving at that index. And then it wants to know the individual values that are arriving. So the E macros implement a special functionality where the number of events is always assumed to be 1, which has been working fine for us because we've just been sending a single value down each index. But let's say we wanted a single event bus to hold 3 different values for us. We can also do this as well, and we'll use the B macros to do so. And now that we've replaced our E macro with a B macro, I also want to replace our small raw receiver and our small receive gate with the normal versions of each. And you'll see we're going to have some extra inputs and outputs here. So from top to bottom, these inputs and outputs are the ID of the incoming values, the number of events we're going to receive at that index, the counter at that index. So if we have 4 values that are going to arrive, the counter is going to count 0, 1, 2, 3, and then again the cache symbol will give us the actual values themselves. So let's set this up to have a single index on the event bus receive 3 knobs at once. So I'm going to create a total of 3 knobs that use a combination of order and value modules to set up our event bus chain here. So whenever a knob receives a new value, we're going to store that value, and then we're going to trigger another value of 3 to go to the event bus. And so this is going to tell our event bus to expect 3 values at the given index. And all of these values are going to end up being merged together to go into the same input of our event bus. So let's duplicate our knobs here. And once we've triggered our number telling the event bus how many events are going to arrive, we can trigger each of our values in turn using an order module. So this is just a great illustration of why I don't really like primary. We're using a total of 5 order modules to do this, and it's possible I've overlooked something and there's an easier way, but it still just feels very ugly and difficult. And once we have this set up, we're going to send 4 values to the event bus at once. First the 3 that tells it to expect 3 more values, and then the knobs one by one. So at this point in time, if we simply connect the cache sign to the output of our core cell, we're always going to receive the last value at our numeric readout here, and we can verify that pretty easily. And the other knobs will have no effect at all. So once we've received these 3 different values, we need a way to differentiate between them. And to do that, we can use the tree macro that I created earlier and simply connect the counter to the index of the tree module, and we can split the 3 values apart like so. And we can verify on the panel that they all arrive at the chosen location. Alright, so that wraps up our overview of the multiplexing library in the partials framework. and we'll continue to explore the partials framework in the next video. In this video, I'll show you the basics of using the chain iteration library that is a part of the partials framework. One of the biggest limitations in Core is the lack of an iteration module, and it's this limitation that the chain iteration library was designed to work around. So typically, if you want to use iteration in Core, you have to create an iteration module and run the events into your core cell. The problem with this is that if you want to use more than one iteration in a given cell, then you need to create multiple iterators. They all need to know how many events they want to have, which might be being decided in the core cell itself. So it just kind of creates all these complications and looks really ugly, and it's kind of hard to keep track of. And the chain iteration library was designed to work around that. So there are two primary macros that are a part of the chain iteration library. We have the chain iterator and the audio chain iterator. And today I'm just going to cover the event version, which is a little easier to use. So in order to set up the chain iterator, we have to have two connections between the core cell and the iterator itself. So one of those is an output flowing into the core cell, and another one is an input taking values from the core cell. In addition, the chain iterator has an extra input that triggers the iteration and an extra output that outputs a 1 when the iteration is active and a 0 when it's off. And so basically what this is implementing is a primary iterator with a huge number of iterations. And we're going to send all of these events into a core cell, and the core cell will take as many events as it needs, and when it reaches that limit, it'll tell the iterator to stop. And inside Core, we have a bunch of macros we can use with these signals. So the easiest iterator to use is called the raw iterator. And we can simply connect the inputs and outputs like so in order to make it a part of the chain iterator. And we have a single other input that tells us the number of events we want. And the cache sign at the output here is going to give us a number of events equal to our input. They're going to start at 0 and they're going to increase by 1. So the way we have it set up right now, we're going to get 16 events from 0 to 15. So I'm just going to create a button to trigger that. And I'm going to use Event Watcher to look at the outputs of this to make sure everything's working okay. And if you don't have Event Watcher, you can download it from the Reactor user library. It was uploaded by Chris List. And you can see when I trigger the iteration macro, we get our 16 events. So the cool thing about chain iteration is that we can use another iterator after this and have the events happen in order. So if I create another partials framework macro called an iterator and connect it to the iteration chain after the first iterator we created, this one works slightly differently. So we can tell the number of events, the starting point for the events, and the increment for each subsequent event. So now we're going to have 16 events starting at 100 and increasing by 3. And if we create a new output to look at these events, we'll see that they happen after the 16 events from the first iterator. And this is pretty great for us for a few reasons. First of all, we're able to create several iterations inside Core with a single iteration module. Another thing that's really great is it's really easy to control the order of events as they happen. So if we were using like a couple different iteration modules, and we need to use order modules to trigger when they happen, and it just kind of creates ugly code and a bunch of different core inputs to our cell and etc. Okay, and another macro I'd like to show you is the output filter, which is also a part of the iteration library. And this should just be the last macro in your chain iteration core cell. And I'm not sure exactly how it works, but according to Max Ziegler, who created the partials framework, it is there to save you some CPU. Another type of iterator that we have access to is the for loop. And these are very common in text-based programming. Typically you use an A is less than B loop. And so basically what this says is you're going to supply a value for A and B, and for each iteration you'll check to see if A is less than B. If it is, then you continue the loop, and if not, you end the loop. So if we set A to 0, B to 4, and the increment to 1, we should get a total of 4 output values for any loop that we have. Those 0, 1, 2, and 3. However, you'll note that's not quite working with our current setup, and the reason for that is that the for loops in the partials framework work a little bit differently than the other iterators that we've been using so far. And so since the way we have it set up, the value of A is incrementing by 1 for each iteration, we need to reset A whenever we want another loop to start. And to do that, we can use the question mark output from the chain iterator macro. So that value is going to turn to 1 whenever we have a new iteration triggered at the trigger input of the chain iteration macro. So we can check that event value to see if it's greater than 0, and if it is, we can reset A to 0, and this way we'll get an iteration each time we trigger our chain iterator. Alright, so one last thing I want to cover about the chain iteration method is we can also do what are called nested loops. And a nested loop is what you get when you trigger one iterator module with another iterator. So you can try this in primary too, of course, but this whole core setup is pretty interesting as well. So these use for loops exclusively, and to begin with we use a for loop like we've just set up, and then if we want to create nested for loops inside that for loop, we use the nested iteration macros. So these nested iterators have some different inputs and outputs than our normal for loops. So most notably, we don't have the chain iterator minus plus and plus minus inputs and outputs that we would use to connect this to the greater chain. Instead, we have these kind of squiggly parentheses here that are used for begin and end statements in text-based languages such as C++. So just like with the ordinary for loops, we want to trigger the A value every time a new loop starts. And for a nested iterator, the new loop is going to start every time we receive a value from the previous loop. So we'll use the output of the previous iterator to trigger the A value. And finally, we have to connect from this for loop back to the original loop that we're nesting from. So that's just telling our original loop that our loop is finished here and that it can continue iterating. And just to see how the order of events is going to play out, I'm going to connect this second iterator to our event watcher as well. And you'll see we first get an event from our original for loop, and then the second for loop iterates all the way through. Then we get a second event from our original iterator, and then our second iterator goes all the way through again, etc., down to the end here. So I know that the way these for loops are connected seems a little odd, and It might be a little confusing at first. I definitely had a hard time figuring it out. But the partials framework comes with a bunch of documentation, PDF files as well. That the one that focuses on the chain iteration method has a bunch of different examples of nested for loops and how they work and how to set them up. In this video, I'll show you how to use the sine engine and the modal engine, which are two macros you can find in the partials library section of the partials framework. These macros are designed to connect to the sine and modal banks, respectively, and they take care of a lot of behind-the-scenes stuff that you probably don't really want to deal with yourself, and they provide a very powerful framework for creating new synthesizers using the bank modules. For the purpose of these tutorials, I'm going to focus on the sine engine, which is just slightly easier to program and use, but the same concepts will apply to the modal bank as well. So connecting the sine bank to the sine engine is pretty straightforward. We have outputs from the sine engine for index, ratio, amplitude, and phase, and we can connect them all directly into their respective inputs on the sine bank. And the sine engine macro itself has a lot of information that it needs the user to provide. So I've created another macro with one output for every input in the sine engine, and those can simply be connected directly. So this is just giving the engine the information it needs to control the sine bank properly, such as the number of sine oscillators and the incoming pitch, etc. And this macro also has three outputs that are meant to be wired directly into the sine bank. So the number, the pitch, and the apply outputs can all be wired directly into their counterparts on the sine bank. Alright, so let's look at a very basic kind of default setup for our empty macro here. I'm just going to show you a really simple way to do things, and you shouldn't be scared of experimenting and adding new components. So for starters, for example, I'm just going to create a constant value that's going to supply the number of sine waves for our sine bank to process. And obviously, instead of a constant here, you could use like a knob so the user could control how many partials there are or whatever. I'm just making something really easy. The next two outputs are going to control the range of the partials that are affected by our partial engine. So if we have 32 partials, as I've already specified for the first output, and we want our sine engine to affect all of them, then these values will be equal to 0 and 32. If you wanted the sine engine to only process half of our partials, you could set the third output to be equal to 16, for example, and then it will iterate between the values of 0 and 15. And next up we have our pitch output. The simplest way to do this is simply to connect it to a note pitch module. You can of course add or subtract values here to change the octave or whatever. The rate output we'll talk about in a little bit. The V and VCS outputs can be connected to the events from the voice info module with the same names. So next up is the ranges output. This one is a little bizarre. So if this is equal to 0, then the partials will all be processed every time. You'll ignore the second and third outputs. And if it's equal to any other value, then you'll use outputs 2 and 3 to control the range. So typically you can leave this at 0 unless you're doing something pretty complex. And next up we have the rout output. It's not very well defined in the partials framework documentation, but it does suggest you set it to -1. And it mentions that when this value is equal to -1, the sign engine will not be sent any unnecessary values. So for example, if you have your ratio of your second partial set to 3, and you do an update and the ratio is still equal to 3, then that event will not be sent to the sign bank, and it'll just save you a little bit of CPU that way. So typically you can just leave rout set to -1 and leave it there. Next up we have the trigger X output, which you can just safely ignore altogether. It's just a kind of more complicated and very special use output. After that we have the update output, which I'll show you how to use in just a moment. And next after that we have the debugging flag. So this is going to tell us how the debugger in the sign engine works. If it's set to -1, we can get values from all of our partials. If we set it to a value between 0 and number, the first output, then we can get values only for the specified partial. And if we set it to anything greater than number, then we're going to end up turning the debugger off altogether. The B output here is going to end up being our event bus that carries all of our necessary data into the sign engine. But first let's make use of the update, the rate, and the apply outputs here. They're all going to kind of work together. And in order to use these, we can use another partial framework macro called the CR clock. And this is just going to be an update clock for our engine. So we can give it a constant frequency here. If you want to have a variable update clock, you can of course just use a knob, whatever. And we're going to take the events coming out of that macro, and we're going to use the order module to make sure that we update all of our partials first. And when we're done with doing that, we can apply the changes that we've made. And the rate output can be connected to the rate output of the CR clock. And we also want to have the apply output triggered whenever a new gate is pressed. And the reason for that is we want to restart all the signs with a phase of 0, and we want to set the pitch to whatever our new pitch value is going to be. So let's create a gate and a separator. And only when the gate is greater than 0 will we use it to trigger the apply input of the sign bank. Alright, and lastly, I just want to create a macro to hold our event bus. And inside we can just hold a single multiplexer that can pack any parameters that we want to send into the sign engine, into the event bus. And that way, whenever we want to get a new value into the sign engine, we don't need to create 50 new inputs and outputs on all the nested macros all the way down. We can simply throw the value onto the event bus and then grab it where we need it. And I'll show you how that works in the next tutorial. Alright, so that's how to set up the sign engine and the sign bank to work together. I know it's a lot to take in at once, but most of these values are pretty self-explanatory or pretty easy to set up regardless. So in the next video, I'll show you how we can use the sign engine to get some interesting waveforms out of the sign bank. sign engine all set up, let's dive into the insides and take a look at how it works and talk about how we can create our own macros for use with it. So to begin with, let's take a look at the engine control macro. And this is the primary part of the sign engine, and it's made up of two basic components. The first is the chain iterators, which we talked about a few videos ago. The sign engine has two chain iterators to work with. The top one is triggered by the trig_x input that we ignored in the previous video, so we won't be using it. And the bottom one is triggered by the update input. And if you'll recall, in the last video we set up the update clock to have a frequency of 100 Hz. So this iterator is going to be triggered 100 times a second. And the other part of our engine control macro is another little event bus here. And this is just going to store all of our parameters like the number of partials that we have and the incoming pitch, when the update clock gets triggered, etc. So far we have two chain iterators, only one of which we're going to use, and two event buses. So when we check out the core section, both of the event buses are going to be merged into a single event bus pretty much immediately. So this is pretty cool. Whatever data we might need inside our core cell, we can access it just via a single connection. And so this is just going to save us a lot of wiring later on down the line. And most of the rest of this core cell we're not going to need to worry too much about. We have some overhead macros, these two guys here. There's a debug macro at the bottom and the chain iteration filter at the top. And all the real interesting stuff is going to be going on inside the partial stream edit layer, which is where we get to do all of our work. So let's take a look. And this macro is going to receive all the other stuff that we've set up so far. So we have both of the iteration clocks. We have another clock for controlling the partial stream that's been created from our main iteration clock. We have a giant array named P that holds all of our partial data. We have the debug array, and we have our event bus stream as well. So we can access any information about what's going on in our ensemble from this macro, basically, or any information that we want to be able to access anyway. And the partials library has a ton of macros that we can use to quickly create our own sign processors. So to access those, we can go to the partials library section and into the partial processor. We have the modal processor for modal banks and the sign processor for sign banks. They're going to work almost identically, but let's check out the sign processor. And so hooking this up should be fairly self-explanatory. We have a clock input, a P input, and a B input, and the blank input at the bottom we can ignore. It's just for any other information we might want to grab from core or something. And once the clock signal goes through the sign processor, the new clock signal will come from the output of that sign processor. And using this clock signal like this allows us to control the order of events, because if we attach another sign processor to the output of the first, then that one will have to be processed after the first one. So by now you're probably pretty sick of all these nested structures and how complex everything is with the partials framework here, but we're almost at the bottom of the well. So the sign processor has a few overhead macros that I'm just going to pretty much ignore completely. We just have to trust that they do what we want them to do, which is basically to unpack the event bus and the partials array for us and gives us access to them. But we have two macros that are doing all the work. The first is the algorithm macro, which is going to receive all of our relevant data, and then we can make changes to it and store it in the array by sending it to the output. And we have another macro that is designed for grabbing all of our necessary data from the event bus, or from other places in Core, as we'll see eventually, but not in this video. So we're almost ready to start programming here, and there's just one thing left to do, is to add some knobs to our event bus so we can ship some values into our sine engine for us to use. So I'll just let those stay named as 0 and 1 for now. And their IDs on the event bus are going to be numbers 50 and 51. So I'm going to go into the get arguments array here, and we have already unpacked the event bus in the previous macro, and so we have all the event bus information coming in, so we can go into the multiplexing library and grab ourselves a receiver. And you can of course use the kind of built-in structure they have for this, these two receive macros, but I just find those to be a little complicated, especially for something as simple as grabbing something off the event bus. So I'm just going to do it like this. So this first one here, we're just going to say we want to be grabbing something from ID 50, and we'll give all the relevant inputs here. And we only need the value output at the bottom. That'll be for our first knob, and we can just duplicate the whole structure for our second knob. And once we have these made, we can connect their outputs to the inputs of the algorithm macro. And it's just a really easy way for us to grab all of our relevant information and ship it where it needs to go with a minimum amount of wiring. And the reason I didn't use this kind of built-in structure here is I just find it to be kind of clunky. It's mainly used for when you have values coming from the event bus and from maybe from somewhere in Core as well, and you want to be able to send them both to the same location, which is just not what I'm trying to do here, and I just find the interface of it to be a little confusing, so I just would rather use the basic multiplexing macros. And we're finally ready to start programming in our algorithm macro. So we have our two inputs here, and I don't want them to do anything when they arrive. I want them to wait in a latch. So I'm just going to store them in a modulation macros. They're both going to end up being multiplied by something, so I'm just going to store them in the bottom half of a multiplication modulator here. So I'm going to use the bottom input to control the ratios of our sine bank. And the ratios control what frequency a given partial is going to play back at. And the ratio is directly related to the main pitch input of the sine bank that we give it. So if a ratio is equal to 3, then it's going to play back 3 times faster than the base pitch. By default, each partial has a pitch that's equal to its index number, so index 7 has a ratio of 7. And I just want this knob to be able to either spread them out further or crunch them closer together again. So we're basically going to multiply it by index minus 1, and then we're going to add 1 to the output, and that's going to be our ratio. And so that'll make it so our first index will always have a ratio of 1, and we'll always be playing back at our base pitch, and then the other sine waves will be related to it, determined by the knob that's connected to this input. So that sets up our ratio, and we can just send it to the ratio output. And I want to set the phase of each of our partials to be equal to 0, which is boring but simple. So that's easy enough to achieve with just a latch. And finally, we want to be able to calculate our amplitudes. So I'm going to multiply our ratio by another knob, and we're going to take the cosine of the output. And this doesn't really have any rhyme or reason to it. This algorithm I'm about to show you is just something I kind of tossed together fooling around and seeing what it would sound like. So took the absolute value of the cosine, and I'm going to multiply it by index over 1 over index, sorry. And so multiplying it by 1 over index is just kind of making sure that as our partials get increasingly higher in pitch, that they're going to be lower in amplitude, and that just makes it so we don't have these really irritating high-pitched sounds going on, which rarely occur in real objects anyway. So the spectrum of the sine bank that we just declared is going to look kind of like the absolute value of a cosine that gets smaller as the frequency gets higher. And I'll show you that in the next video. So we can set the values of our knobs here. I'm just going to set the first one to have a range from 0 to half of pi. And it's half of pi because it's being directly related to the cosine wave. And the bottom one, I'm going to have a minimum value of 0.5 and a maximum value of 4 and a step size of 0.5. And this is going to kind of sound like an octave shift a lot of the time. Alright, so in the next video, I'll just show you what the output of this ends up looking like, and I'll show you how we can improve it and some more complicated things we can do with the partials framework. Alright, so I've added some basic elements off screen, volume control, and a very basic envelope, as well as an FFT and an oscilloscope. The CPU usage has gone up, but that's just because I'm using this very expensive FFT module here. So let's take a look at the waveform that we created last time. They look pretty interesting, but when the cosine knob isn't moving, they sound kind of boring. Alright, so let's make this a little more interesting and jump back into the partial stream. And in this video, I'm going to look at a class of macros called bank modulators, which you can find in the partials library. And these are components that are used to affect every single partial in a sine bank in the same way. So we have, LFOs and envelopes to work with. They're very easy to connect. Just connect the bus and the clock quick buses. And you can ignore the bottom two inputs. We're going to be receiving those values via the event bus. So we can connect this macro directly to the empty input on our sine processor. And we'll do some more with that in a bit. But first, let's hop into here and make sure we're receiving our proper values from our event bus to make the LFO work properly. And in doing so, you can get a kind of good idea how the makers of the partials framework wanted you to set up the getArguments macro. So for each value that we want to be able to grab off of the event bus, we have one of these little question mark macros here. And the top input is the ID value coming from the event bus, and the bottom value is going to be which event ID we want to be able to grab. And the Boolean value coming out of the question mark macro is used to control a receive gate, and there's several different custom types of receives within here. They all work very similarly with minor differences. But it's a good idea to look at the bank modulators and the other macros available in the partials library and see how they work, and it just can give you a lot of ideas on how to set things up on your own. So once we have our sine LFO into our sine processing macro, there's not a whole lot left to do. It's going to flow directly into this sync in macro by default, And, we could probably just pass it all the way through here. I'm not sure. But we have a special macro to use with this called a smart value. And the smart value is exactly like a primary value, with the difference that if you send a trigger value to the top event and there has not been a new event received since the last trigger, then it won't send an output. And so to trigger this module, we're going to use the quick bus called loc, which stands for local clock. And that'll get triggered for every new partial. However, we're only going to receive a new LFO event once per update, and so most of the triggers will end up getting ignored. And by default, our value is getting sent next into this merge module, which is completely empty, and is really only for values that we're trying to receive both from primary and from core simultaneously. So I'm just going to delete it and connect our value directly into the algorithm macro. And once we have it inside our algorithm macro, we just need to decide what to modulate with the LFO. So I'm just going to multiply it by the value flowing into the cosine. So we can duplicate this multiply macro here. And next, let's take a moment to make sure that everything's connected all the way down. And the next thing we need to do is create a knob that will be received at index 52 to tell the sine LFO what its frequency is. So let's create a new knob, and I'll give it a minimum value of 1 and a maximum value of 5. You can kind of choose whatever values you want to, of course. And the next topic I want to address is thread safety. Thread safety is a very esoteric and complex issue that is rarely of any importance at all when you're working in reactor, but with the partials framework, we're kind of pushing up against the boundaries of what is possible with reactor, so we run into a few problems. And the issue is that events that are caused by the reactor panel, such as when you're turning a knob or another element, are on a different thread than events that are created by reactor modules such as an LFO or the system info module. And on rare occasions, one of those threads can interrupt the other one before it's done processing. And so when I first started working with the partials framework, getting some really weird errors that I couldn't figure out, and eventually realized were caused by the event bus no longer working properly. And I eventually tracked this problem down to thread safety, and as it turns out, there are some macros that come with the partials framework to help us deal with this. And so namely, we can use the smart value macro, which is a primary version of the smart value macro that we used earlier in this video. And so we'll store every knob or other panel element in a smart value, and we can trigger them with the control rate output of a system info module. And that way we'll transfer all of our events from the panel thread or the GUI thread to the processing thread. And there is a document that explains the whole issue of thread safety. Unfortunately, for some reason, it's still not bundled with the partials framework, but you can find it on the Native Instruments Reactor forum by searching for the word thread safe, one word. So now that our frequency knob is set up, that should do it for our LFO, and we can just confirm that everything is working. Alright, so that's how you use bank modulators, and in the next video I'll show you how to use another class of partials framework macros. In addition to the bank modulators, we also have partial modulators, which have their own menu in the partials library. And these are modulators that effect every partial in a sine or modal bank separately. So you can have, for our sine bank that we have with 32 different sine waves, we have 32 different LFOs effecting each one separately. And these are very easy to connect. We just have to connect anything that has the same name as one of the quick buses, and then we can just ignore the other inputs. They're just values that we're going to grab from the event bus. And how the event bus works is going to be a little different than with the bank modulators. So let's look at the sine LFO we added last time, and you'll see that we're receiving single values from the event bus. And if we look at the get arguments macro in the partial sine LFO, we have a much more complicated receiving system here. So we're going to write all of our values into an array for each frequency value of each partial LFO, and then we're going to read them out as we calculate each partial separately. So this means we need a way to write our 32 different frequency values into the event bus. So to do this, I've made a new macro that takes the number of sine waves as an input, and we're going to use it in tandem with one of the B event bus macros, which allows us to send blocks of data at a time. And so if you recall, the way that we do that is to first tell the event bus how many events to expect at a single input, and then we have to send it that many events. So in order to do this, I've set up an event table with 32 values, and we're going to read it using an iteration module. And before we start reading, we'll send out a value of 32. Then we can send these values directly into an event block macro. And this setup works okay. The one problem is we have to draw our values in, but then they don't become active until we hit the right button. So for a more polished project, I might make something a little more sophisticated, but since we're not concerning ourselves really with primary in these videos, I think this will work just fine for now. And in order to make sure these events get where they're going, we need to tell the event bus which ID to expect them on. So we just fill in the number here as 60. And all we have to do now is to wire our new sine modulators into our sine processor. So again, we can use a smart value to receive this. And we'll just give it its own inputs and outputs to the get arguments macro. I mean, you could probably just run this directly into the algorithm macro, but just to keep with the whole partials framework paradigm, we'll do it their way. Alright, so I'm just going to do something, pretty boring with this and use it to affect our spread knob, which is coming in right here. So I'm just going to take the absolute value of our LFO, since we always want the spread to be positive, and then we'll just multiply it by the spread and use it as we were before. And this isn't going to be terribly exciting, but it'll give you an idea of what the partial modulators can do and how to use them inside a sine engine. Alright, so that's about all we have time for. Again, the partials framework has a ton of documentation that it comes with that has a bunch of pictures and examples of things that you might want to do, so it's pretty useful to check that out as well. I certainly wasn't able to go over everything that I would like to have in the partials framework. It's just a huge subject, and a lot of it is pretty hard to grasp. So thank you for watching these videos, and if you have any questions or suggestions or things you'd like to see from me in the future, please don't hesitate to get in touch with me at salamanderanagram@gmail.com.